Hi, this is Mrs. James, and this is our last-minute review for several topics for our end-of-course exam. This is Nuclear Chemistry Part 1. The teacher showing this recording might want to stop it occasionally to give the students time either to listen or to watch or to fill in blanks. So you can just pause and restart as is necessary. Nuclear chemistry. We previously in class have studied chemical reactions. Chemical reactions are about changes that involve electrons, either transferring them or sharing them, and remember that electrons are outside the nucleus of an atom. With our focus now on nuclear reactions, we're talking about changes that happen actually inside the nucleus itself. Now, nucleus is singular, this word here, nuclei, is plural. So all it means that instead of the electrons going through some kind of a change, the nucleus itself is going through a change. Both types of reactions involve energy, but nuclear reactions involve a lot more energy for reasons that we'll talk about later. Alright, nuclear stability. Some isotopes of some elements are what we call unstable. So let's give a little bit of background before we try to define that. Why do electrons hang around the nucleus? Why don't they just go flying off into space? Well, you know that opposites attract, and the negative electrons are attracted to the positive protons inside the nucleus. And we call that force, which is a field force, an electromagnetic force. Another field force that you're familiar with is the force of gravity. Field forces mean that the objects don't have to be in contact for that attractive or repulsive force to be working. Well, there's also a field force that's working inside the nucleus. It's not the electromagnetic force, it's not the force of gravity. It's what we call the strong nuclear force. The strong nuclear force binds protons and neutrons together. Now, they shouldn't be attracted to each other because one is positive and one is neutral. So it's not the electromagnetic force, it's a different force, strong nuclear force. Think about it. All those protons inside the nucleus, they all want to be repelled from each other. They're trying to push away, but the nucleus still stays together. There has to be a reason for that, and that's because of the strong nuclear force. At a close distance, it's very strong. It's a stronger force than that force that's trying to push the protons away from each other. So, in close quarters, the strong nuclear force trumps the electromagnetic force. When these two forces aren't balanced, then the nucleus is unstable. Through radioactive decay, an unstable nucleus emits radiation in the form of fast-moving particles and energy to produce a new nucleus. This means it's either changing what isotope it is or what element it is. Nuclei that go through this are called radioactive. So let's review this. We have unstable nucleuses. They're unstable because the balance is off between the strong nuclear force and the electromagnetic force. When this happens, the radioactive nucleus goes through radioactive decay and it spits something out so that it becomes more stable. The radiation that's released can cause detrimental effects, but it also can be harnessed for use. There are multiple types of decay. We're going to mention just a few of them. The first one we want to talk about is called alpha decay. So remember, this is something that gets emitted from an unstable nucleus. An alpha particle is 2 protons and 2 neutrons. That's what gets spit out of the unstable nucleus to make it more stable. So let's take a look at the periodic table. 2 protons and 2 neutrons get spit out. Well, if 2 protons get spit out, the element actually changes what element it is. So here's an example of an element that goes through alpha decay, tellurium. If tellurium goes through alpha decay, it loses 2 protons and it turns into tin. So it only will have 50 protons instead of 52. So nuclear decay actually changes the element into a different element in this case. Uranium is another one. When uranium goes through alpha decay, it loses 2 protons and it turns into thorium, which only has 90 protons instead of 92. So those are examples of alpha decay. Another kind of radiation is called beta decay. This one is a little bit more complicated. Let's pretend that this circle right here is a neutron. Well, a neutron isn't really what you think. A neutron is actually composed of two different things. Let's think about this for a minute. A neutron is neutral. If it's composed of two things put together, one of them has to be positive and one of them has to be negative. What do you think those two things can be? A proton and an electron. So sorry about my kind of messy picture here. I'm sure you can do better in your notes. So a neutron is actually a proton and an electron attached to each other. During beta decay, the electron part of the neutron gets emitted, so it actually leaves the atom and the extra proton stays behind. So what does that do to the atomic number? Well, it makes the atomic number greater by 1. So it still changes it to a different element, but it changes it to an element that is higher on the periodic table instead of lower. So carbon is an example of an atom that goes through beta decay. When carbon goes through beta decay, it turns into nitrogen. Another element that does this is copper. When copper goes through beta decay, it turns into zinc. So it has an extra proton. Two other types of radiation are gamma radiation and neutron radiation. Gamma radiation is all energy. Neutron is neutrons being actually emitted. And we may talk about those later when we revisit this topic at the end of the school year. But right now we'll just focus on the alpha and the beta. Alright, the next thing that we want to talk about is something called half-life. When something goes through decay, the element that we start with is called the parent, and it changes into what we call the daughter element. The term half-life is about the rate at which this change happens. Now again, please pause the video if you need more time to write these down. Here's a graph that we can use to help us understand half-life. On this graph that I have right here, on the x-axis I have the number of half-lives, so 0, 1, 2, 3, 4, and you can have more half-lives than 4, it can keep going. And on the y-axis we have the percentage of the parent isotope remaining. So at the very beginning of a nuclear reaction, and let's say it's our copper turning into zinc. Okay? This is our parent, this is our daughter. So in the beginning, it's all copper. After one half-life has gone by, this is our new ratio. Half of it is still the copper, and half of it has turned into the daughter, which is zinc. Remember, we don't have to be talking about just copper and zinc. I'm using that as an example. Now, after another half-life has gone by, let's look what we have here. We're down to 25% of our parent copper, and the rest of it is our daughter zinc. And then after 3 half-lives have gone by, we are down to 12.5% is our parent, and the rest of it is our daughter. So what's happening here is that with each half-life, half of the parent that's left turns into the daughter. In other words, our rate of decay slows down as time goes on. So, after 1 half-life, half of the parent is left. After 2 half-lives, 1/4 of the parent is left. After 3 half-lives, 1/8 of the parent is left. After 4 half-lives, 1/16 is left. After 5 half-lives, 1/32 is left. Now these years are only for that specific element. This is talking about carbon-14 decaying. It happens to have a half-life of 5,730 years. Here we are just looking at it in a different format. Now it's looking at it in terms of grams, so we could actually talk about how many grams we have of the parent and the daughter. And here we are just looking at a nice chart so you can see that curve. You're going to have to continue on part 2.